All right, so we're going to do the Mars rover together. Here we go.
Oh, wait. No.
So first I want to determine the acceleration due to gravity on Mars in terms of g on Earth. Well, I know that the force of gravity, the magnitude of the force of gravity, so I can ignore the negative sign, is m1 m2 over r squared. So since I'm going to express the acceleration on Mars in terms of the acceleration on Earth, I'm going to write an equation for those. I know that that the mass of the sojourner is equal to the weight. So on Earth, it's mg. And I know that its mass on Mars is the same. And it's equal to the force of the gravity on Mars divided by the acceleration on Mars. So let's say the force of gravity Mars divided by the gravitational acceleration on Mars that's the mass, right, on Mars. So that equals the mass on Earth.
The weight on Earth. Well, yeah. It's the same mass anywhere.
Right. Okay? So what is that? Well, the force of gravity on Mars is big G, mass of the satellite times
It's a rover vehicle.
mass of Mars. Okay, rover, whatever. What do you want to call it? Well, we'll call it S for sojourner. All right. Times or over the radius of Mars squared.
Why?
All right. And that equals big G, the mass of the sojourner, times the mass of Earth over the radius of Earth squared over G. So big G's cancel, I can get rid of that.
So sojourner.
And the mass of this sojourner cancels.
And then radius of Earth is 1.
All right. So what I'm going to do is I'm going to say the radius of Mars in terms of Earth's radiuses. So I'm going to substitute in here. Let's move over here. Mass of Earth over radius of Earth squared. And the mass of Mars is 0.11. Oh, forgot the G. Here's the G.
Wait, why is there a G?
Because, oh, and I forgot the G here. G Mars. Because I'm going to get G Mars in terms of this G. That's why I'm leaving it there. So 0.11 Earth masses over the radius of Mars is 0.53 Earth radiuses. G Mars. So now I can say, well, G Mars then is divide out by mass of Earth, and I can divide out by radius of Earth squared, and I get 0.11 over 0.53 squared, multiply both sides by g, and I get that the acceleration due to gravity on Mars is 0.11 over 0.53 squared g's. So what's 0.11 over 0.53 squared? So the acceleration of gravity on Mars, the acceleration due to gravity on Mars is 0.39 g's. So now, calculate the Sojourner's weight. Well, what is its weight?
Normal. On Mars.
It's mg, right? It's the weight, it's the force due to gravity on Mars, which is ma, using that acceleration. So mg is, on Mars, is m, the acceleration due to gravity on Mars. Right? That's just F net equals ma. I know the mass is given as 11.5 kilograms times 0.39 g's, which is 3.9. So what's 11.5 times 3.9?
4.5.
Who?
11.5 times 0.39 equals...
Well, the times 10, so 3.9.
Oh, yeah, okay.
Who? 40? 45? 45 newtons is the weight on Mars. Now, assume that when leaving the Pathfinder, the Sojourner rolls down a ramp inclined at 20 degrees. Well, okay, so now it's going to go down it's going to roll down an incline.
We're doing a normal problem, but all in different gravity.
All in different
Yeah.
world.
Exactly.
It's like weird.
So, mg Mars, normal, right? So what do I need? An F net y, which, how am I going to set my coordinates system?
By the acceleration.
Which is,
Normal.
mg Mars.
Well,
Right?
just by normal.
because if the Sojourner is accelerating, it's accelerating in the direction of the ramp, right? So I want that to be one of my axes. So F net y equals n minus
Cosine?
yes, mg Mars cos 20. And it's not going to come off the ramp, so that's going to be 0. So, because the acceleration in the y direction is 0. So n equals mg Mars cos 20. Well, we just found that mg Mars is 45 newtons. So 45 newtons times cos 20.
42. Yeah,
Who?
yes.
42. So the minimum normal force is 42 newtons. And D is one of those rare gems, what we call a Gemi.
0.
What is the net force on Sojourner as it travels across the Martian surface at constant velocity? 0. Justify your answer. Well, I know that F net equals ma, and A is delta V over T. So if V is constant, delta V is 0, therefore A is 0, therefore F net is Determine the maximum distance that Sojourner can travel on a horizontal Martian surface using its stored energy.
Oh,
Well,
stored energy available. 5.4.
okay, yes, we're going to use that stored energy that's available. Am I done with all these numbers? I think so. So I know that I'm going to use something about this energy that's stored at 5.4 times 10 to the fifth joules. And then what else? I'm looking for a distance and so what else is given that you think might be helpful? Yeah, the power under normal driving circumstances is 10 watts. Now, how am I going to relate this to that to that? Well, why do I need 10 watts of power to keep it moving at a constant speed on a horizontal surface?
Dust storm.
There's friction and air resistance, dust storm resistance. There's work done by non-conservative forces. And the work done by non-conservative forces is going to equal what?
Wait, no. Yeah, it's constantly.
Okay. It's going to equal all that energy. We're going to run out of energy when the work done by non-conservative forces uses up my available energy.
Yes.
Well, what's this power then? This power is the drive power. If it's a constant velocity, then it's also the power of, it's the rate of this work, right?
Yes.
It's the power of the non-conservative forces. All right? Well, what does power equal?
Time.
Work over time,
Or FV cosine theta.
also written as FV cos theta. Well, if we're moving along horizontally, the drive force and the velocity vectors are
0. I mean, that's 1.
the angle between them is 0, that goes to 1, right? They're collinear. So I know that the power is equal to the driving force, which is also equal to the non-conservative forces, because they're balanced, times the land speed. So I can say that force, driving force, which is also equal to the non-conservative forces, is the power over the land speed, which is what? 6.7 times 10 to the negative 3? 10 over 6.7, oh, no, yeah, 10 over that.
So that would be just 6.7 times 10 to the 4th.
Inverse. What is 10? Who? 1,493.
So that's the force.
That's the drive force, which is equal to the frictional force, right? If I draw a force diagram, it looks like this. There's frictional forces, drag forces, whatever, and they're equal to this pushing force that's getting me along the Martian surface. So I could call these non-conservative forces because they're equal to the drive forces. All right? But that still doesn't answer our question. Our question was, how far does it go? Well, what does work equal? which we already said is 1. So that 5.4 times 10 to the 5th divided by that F of 1493 will give me the maximum distance.
Where did you get 1493? Wait,
The power divided by the land speed?
10 over 6.7 times 10 to the negative 3.
Yes. 362 meters? That didn't seem very far.
Oh, okay. Well, makes sense. It's not supposed to go.
Yeah, I mean, I'm not downing you. Just seems like we're getting ripped off. I mean,
It was only 1997.
okay, so that's E. What about F? Well, F basically is saying that 0.01% of the power, which we already explained, is for all non-conservative forces. All non-conservative work, energy lost. If 0.01% of that is going towards friction, what does that make the frictional force? Or the drag force? Well, the work done by drag forces is going to be equal to what? Yeah. And so, or I could do it, I could use the power one, right? You could say power due to drag forces is FV. That'd be a better one, because I already have that. Then the power due to the drag forces is 0.01% of the 10 watts. Right? And so I just divide by the land speed to get the drag force. So it becomes 0.0001 times 10 over the land speed, which was 6.7 times 10 to the negative 3.
Gosh, that's like, so, hold on.
This is a hard question.
It's a penny.
I would agree. What does that make that frictional force then? Or that drag force?